Hi everyone. So today we are kind of wrapping up our conversations about graphs of polynomials, and this is just sort of some odds and ends. You'll notice the title of the lesson says Fun with Quadratic Polynomials. Not all of these are going to be quadratics, which is why I threw the other in there. But kind of the methodology is the same for all of them. So in this first example, it's instructing us to graph this thing and then use your graph to identify these. I think I would actually prefer for us to talk about how to find them algebraically, because once you cut out all the blah, blah, blah coming from me, doing this by hand is really not nearly as hard as it sounds, and you could probably do it faster than you could even, create a graph of this thing. So looking at this function, first of all, I hope that you can recognize that this is going to be a quadratic. This is going to be a parabola when we graph it. Because if I were to FOIL this out, I would end up with an x squared in there. Okay, so this is a quadratic. It's going to be a parabola. And so if I'm looking for the x-intercepts, I just want to remind you that x-intercepts are really the same as the roots. And that's what we've been talking about for the last few lessons, is this relationship between the roots and the factors. And this equation is written in what's called factored form. So really, the roots should come very easily from the factors. You should be able to look at this and say, I know there's a root at x equals 7 and a root at x equals 5. Those are my two x-intercepts. I'm just going to remind you real quick of mathematically why that's true. X-intercepts are always found by making the y value equal to 0. So if I make this a 0 over here, then what I'm saying is something times something times something must equal 0. And that means that either this something or this something has to equal 0. We know the -2 can't equal 0. So one of these two things has to be equal to 0 to make this happen. So the math that I'm doing, and again, I would not expect for you to actually have to write this out, but the math that I'm doing is this. I'm saying, what would make x minus 7 equal to 0? Oh, that would be an x equals 7. And what would make x minus 5 equal to 0? Oh, that would be an x equals 5. So these two values here are my x-intercepts. Now, like I said, I just spent a lot of time talking about that. My hope is that you could look at a question like that and go, oh, I'd have an x-intercept at 7 and an x-intercept of 5 really quickly. Okay? So now let's talk about y-intercept. The y-intercept, just like the x-intercepts are when y equals 0, the y-intercept happens when x equals 0. So what I'm going to do is make the x be a 0. I'm very literally going to say this is -2 times 0 minus 7 times 0 minus 5, which is really -2 times -7 times -5. And then if I multiply those three things together, I'm going to get -70 as a y-intercept. Okay? So to find the y-intercept, and that's going to be true no matter what your function looks like. So even if this wasn't a quadratic, the y-intercept always comes from making the x be a 0. So now let's talk about the vertex. Now, we've talked about the vertex before. If I gave you a quadratic in standard form, if it was like, 2x squared plus 3x plus 5, and I said find the vertex, you could do that whole h equals -b over 2a thing, and then you could solve for the k value. We did all of that earlier in the year. I want you to think about what that would entail. I would have to take this thing and FOIL it and simplify it and make it look pretty, and then I would have to do all that math to calculate the vertex. I mean, that's quite a bit of work, okay? However, we can use the relationship between the vertex and the x-intercepts to help us out here. So just a real quick sketch here. If I know my x-intercepts are at 7 and 5, let's just put them here and here, we'll say. And by the way, I also know this parabola is going to be upside down because that 2 is negative. So I know that my parabola is going to look something like this. Okay, my y-intercept is going to be way down here at -70. But what I want you to notice is the position of this vertex is always halfway between the two roots. Okay, so vertex is always centered between the roots. So for our purposes, we're going to look at this and we're going to say, oh, it's halfway between 5 and 7. That means that my vertex is going to be at, let's see how I'm going to say this, at x equals 6. Okay, that's going to be its location. Now, I still need to find the y value, but I at least know where the x value will be located. It'll have to be located at 6. By the way, that was really easy to do because 5 and 7, I know what's exactly halfway between 5 and 7. Let's say I gave you some like funky numbers where you couldn't tell what was halfway between them. The math that you could do to find that is add them together and divide by 2. Okay? I wouldn't have expected you to have to do that for this one, but you may run into one where you need to. Okay? So if I know the vertex is located at x equals 6, now I just need the y value that goes along with that. So I'm going to plug that 6 into my function. So negative 2 times 6 minus 7 times 6 minus 5. That's going to be negative 2 times negative 1 times positive 1, which is negative 2. Nope, just kidding, positive 2. Positive 2. And so then this and this together make my vertex. So my vertex coordinate would be at 6, 2. Okay? So I found my x-intercepts, I found my y-intercept, I found my vertex. And all of that was with pretty minimal calculations. And like I said, if we cut out all of the blah, blah, blah of me talking in between all of that, you could have really worked your way through that problem very, very quickly. Okay, so looking at example 2 here, a lot of these same things come into play. So you'll notice the first question asks about x-intercepts. X-intercepts are when y equals 0. So if I'm looking at this function and I want to make this thing equal to 0, this is a fraction, right? So we need to think about how do you make a fraction equal to 0? Well, this is going to happen when the top of the fraction equals 0. So I'm going to set this equal. I'm going to say 2x plus 1 equals 0. And then I'm just solving for what x would be. Well, if I subtract 1 from either side, I get 2x equals negative 1. So x would be equal to negative 1/2. Okay, so that's my x-intercept here. Okay, and in this case, I only have 1. So my y-intercepts come from making x a 0. And for that, I'm just going to plug a 0 in for x here. So I'm going to go 2 times 0 plus 1 over 0 minus 1. Quite honestly, I would trust your brain more than I trust your calculator here. You're just going to have to be real careful with parentheses if you're trying to type this in on your own. So I would say this is 0 plus 1, which is 1. On the bottom, 0 minus 1 is negative 1, and then that whole thing works out to be negative 1. That's my y-intercept. Okay. Okay, asymptotes. Asymptotes come from functions being undefined. And when we're talking about fractions, which is what this is, we end up with those undefined values if the bottom of the fraction is equal to 0. You can't have a denominator of 0. So asymptotes are always going to show up in these fraction ones when the bottom of the function is equal to 0. Okay? So what I'm really asking myself here is what would make x minus 1 be equal to 0? Well, that would be an x equals 1. And so this is really representing like a vertical line, and I'm just going to make a note of that. So this is not just a value of x. On the graph, this will be a vertical line that is an asymptote where the graph approaches it but doesn't touch it. It can't touch it because we can't let x equal 1. So now thinking about the domain of the function, and I will tell you, I know that we all hate domain questions, but the domain is really just related back to the asymptotes. Domain is asking what is x allowed to be, and what we just figured out is x can't be 1. We can't let x be equal to 1. So my domain is just all real numbers except 1. Okay. So now as far as sketching a graph goes, I'm going to leave that part to you. I would recommend typing this in on Desmos. These graphs look kind of crazy. And so to be honest, well, I can go ahead and sketch what the graph will look like so that you know if you're seeing the right thing when you type it in on Desmos. But we have a y-intercept at negative 1. We have an x-intercept at negative 1/2. And then we have a vertical asymptote at x equals 1. So this function looks kind of like a hyperbola. It looks like this, and goes down forever. And then it goes like this to the side forever. Okay. Oops, and sorry you can't see that bottom. So that's what it should look like when you look at it on a graph in Desmos. But some of these functions look much different than that. You know, it kind of just depends on the structure of the fraction. So you'll always be able to use Desmos to visualize these. You will want to know how to do the algebra here. You will want to know how to plug in and solve for different values. Okay. Okay, 2 more examples, and the 2 on the back are really quick. So example 3, really, you should already know how to do. If I give you something times something equals 0, the only way to make that happen is to let this equal 0, or to let this equal 0. So then it's just a matter of solving those 2 things. So if I solve this, I would add 3 to the other side and divide by 2, and I'd end up with x equals 3 over 2. Here, if I move the 5 to the other side, I end up with x equals negative 5. So either one of these values plugged in for x is going to give me 0 as an overall value for the function. And that means that those values are the roots of that function. And so then, kind of working backwards from that, if I look at example 4, I'm giving you the roots out front and asking you to come up with the factors. So remember, the factors are always like x minus whatever your root is. So like if I did x minus negative 5, it would look like an x plus 5. So this particular polynomial function would be x plus 3, because I'm doing minus negative 3. I'm going to write this one as x minus 2/3 for a second. There's a reason I'm writing it in light blue, because I'm going to need to fix it in a second. And then x minus negative 5 would be x plus 5. And so really, technically, this is almost your answer. The only thing that I need to fix is we don't ever leave fractions in our factors. So I'm going to take this 3 off of here and slide it in front of the x. And so really, I'm going to call this factor 3x minus 2. But the idea is, if I was given these 3 factors and said find the zeros, if you set 3x minus 2 equal to 0 and then solved it, you would get 2/3 out as an answer. So that's why that works as a factor. Okay, that's it for this lesson. You've got an assignment that goes along with this, and we will talk about it next time I see you in class.